A very good morning. I'm Shubhika Garg, a CMU student taking the computational photography course. I'm here to present my project work titled Wide Angle Portrait Undistortion and Low Light Image Enhancement for Mobile Front Cameras. Let's start with the motivation. Recently, wide angle lenses on smartphones have become increasingly popular, enabling users to capture expansive scenes, group portraits, and immersive compositions. However, broader field of view they provide there's more significant distortions, especially in close-up shots. For example, here we can see that the face distortions look very unnatural. One more interesting thing that you can notice is that facial regions are highly sensitive to geometric distortions, leading to unnatural stretching and squishing. For example, in this image, we can very prominently notice that the face is more distorted while distortions in the background are very less visible. These artifacts can cause images to deviate from real life art appearances and reduce their visual appeal. Another common issue with the front camera is that mobile cameras, particularly front facing ones, often struggle to capture high quality image in low light environments. This is because of the absence of flash in front camera environments. Manually editing these pictures can be very time consuming. Traditional image enhancement methods often rely on supervised methods which require datasets under all kind of lighting conditions. Hence, we aim to develop a robust solution which can work well and handle a wide range of lighting environments. Hence, the overall pipeline motivation is that given a low light distorted image, we then plan to pass it to the low light enhancement module to produce the light corrected image, which will then go as an input to the undistortion module to produce the light corrected undistorted image as the final output. Now, moving on to the method for the wide angle distortion removal. This is a complete pipeline of the method. Given an input image, we first get the segmentation mask using Sapiens, a human vision foundation model. We then use a naive method like called a stereographic projection to see that even though stereographic projections can visually remove distortions in the facial regions, it also distorts background, which can also bend lines in the background, producing artifacts. Hence, ideally, we would want to remove these distortions only from the face regions and keep the background regions intact. Now, moving on to the optimization. In the optimization process, we're trying to optimize a mesh M consisting of vertices Vi where they're minimized using an energy function. The energy function consists of four terms. The face objective term aligns how well the mesh aligns with the detected faces in the image. The regularization term aims to regularize the mesh by encouraging smoothness between adjacent vertices. The line bending term is introduced to prevent shearing and rotational artifacts during the optimization process. The mesh boundary extension is to prevent trivial solutions where optimization results in ineffective or null transformation. Hence, the total energy is then defined as the sum of these individual terms, and then we try to minimize this energy and find the optimal energy vertices Vi. Here are some results. The A represents the input image. We can see that the distortion increases as we move away from the center of the image. B shows the naive way, that is the stereographic projection result. Here, even though the face has less distortion, lines in the background have clearly bended, producing artifacts. C shows our produced result using our algorithm. We can see that it reduces face distortions while keeping the background intact. We also have a visualization of the flow to see that there's more distortion in facial regions while very less distortion in the background region, which is as we desired. Here is the result on one more image producing good results. Now moving on to the self-supervised enhancement method for low light images. Now this is based on Retinix model. The Retinix model is a color consistency model that aims to restore the perceived color of an image, particularly under varying lighting conditions. The core idea behind this model is that image can be decomposed into two factors, illumination and reflectance. Illumination is the ambient lighting conditions that affect an image, and reflectance are the intrinsic color or texture of the objects in the scene which remain constant under different lighting conditions. Now moving to the self-supervised part. So this part is trained such that given an input low light image, it then passes through a deep neural network to produce illumination and the reflectance. Then it is minimized using these three losses. The reconstruction loss here ensures that the product of the reflectance and the illumination closely matches the input image. The reflectant loss ensures that the reflectance has maximum entropy and its aligned with the maximum channels of the low light image. The illumination loss is the structure-aware smoothness loss that encourages consistent illumination. Now here are some results. The left column shows the input image in low light conditions and the right column shows the output image. We can see that our method produces visibly appealing images. Here are some more images. I've particularly included an image in high lighting conditions as well to highlight the fact that the model can deal with both low light and highlight images and will keep the highlight images as they are and not disturb them. Now moving on to some data that we captured on our own. We can see here that the output produced by the low light image enhancement module is not as desired. This is but one such reason to explain this could be because the data set that the model was trained on was mostly consisting of input indoor scenes. Hence, in future, we can possibly try to include more low light facial portraits and then analyze the effect. Because these output images of the low light enhancement modules were not good, this, when given as an input to the distortion pipeline, was not able to detect any face and hence was not able to undistort the faces. I plan to correct them in the future discussion. So moving on to the challenges. One challenge is that the output produced by our low light enhancement module consists of a lot of noise. Here I show one such zoomed in output image. Hence you can see that it consists of a lot of random noise in the background. Another challenge is that errors from the facial detection module propagate to the undistortion module, and hence when no faces are detected, it is not able to undistort the image correctly. Possible future directions to deal with them would be to train the face detection module to work even for low light and noisy images, work on reducing noise in low light image using diffusion models, and then possibly jointly train both the low light and undistorted modules for faster speed and better performance. Thank you.